Thank you so much. I'll throw my T-shirt afterwards into the crowd, you know. Okay. Stage diving. Prepare for the stage dive. Okay. Thank you so much for coming. My name is Dierk Koenig. I work for GNU in Basel, Switzerland. That's it. And the takeaway for this talk is this slide, you know. If it's only this slide that you take with you, I'm fine. Actually, the talk is kind of in two pieces. This is the first piece, 40 minutes, and tomorrow will be the tutorial, 100 minutes. So this is called the introduction. So it's rather high level and addresses the point of why do we want to have this kind of programming. And then tomorrow in the afternoon, if I didn't scare you enough today, then we will go programming, you know. For the 40 minutes today, programming takes a little bit too much time. So there will be only very little programming. Anyway, we will try to make the point why it is important to have this kind of language. Who has been in the previous talk right here in this room? Right, like so? Okay, a few. It was to a large extent, it was in Polish, but I understood some words. And that was the question of artificial intelligence. And if you would ask me what kind of programming language I would use for artificial intelligence, I'd use an intelligent one, but no, I would use one which is based on science, you know? Not necessarily on engineering, only as much engineering as you need, but which has a foundation in science. You're much better off, you're on some very fertile ground if you can base your efforts on science. Who has seen the Martian motion picture? The one that, you know, people live on Mars or one? Okay. This is all about science. And this, the Frege language, which brings Haskell to the JVM, it's all about basing our decisions on science, our work on science. Who has ever done any kind of Haskell programming in his past? Oh, this is like 1/3 of the audience. I'm always surprised how much that is, because until, I guess, 3 years ago, I hardly heard anything about it, leave alone programming in it. But then, after I discovered it, and after I found a way to bring it to the JVM, where I do all my work, which pays my bills, I was very much surprised, not only that it is interesting, but also that it's practical. That's the second point. We program, right? We are all programmers. We need to achieve our goals. We need to make the program, but we'd like to use languages that make it as easy as possible. And a nice language which gives all kinds of benefits and is easy to use, but brings all kinds of benefits, but may not be so easy to use because maybe less practical, then doesn't appeal to us so much. Well, Frege is different. It is fundamentally different. Most JVM languages differ in some way or another. There must always be a point why they differ. So they introduce some other kind of syntactic ways of programming. But most of them are actually superficially different, but follow the same foundation of imperative, object-oriented coding. And only a few ones differ fundamentally. And here we have one that differs fundamentally. This is the main point for today. How much that is different. I'd like to make a short question here. So this is kind of typical imperative programming. That's an imperative program in fantasy language. What is it doing? What is this kind of code doing? For the ones that have difficulties reading, A equals 1, B equals 2. C equals B. Okay, here it gets difficult, right? B equals A equals C. Yes, I know, okay, this is the point where you put off the paper and then make your sketches and so. Any guesses? Yeah, it's Bob's A and B. You know, this is the kind of the thing that we learn first day in programming. This is such a simple thing that we like to achieve, and it is so complicated to achieve, and I'd like to make the point why that is so complicated. You know, here it is. A equals 1, B equals 2. So A and B stays the same when I address a new thing into B, so this is the same. But now the contents of B goes into C, so that moves over there. This was what was happening before in your head, you know. I was looking in your head, and I'm replaying it. Now we are addressing a new value to, we're assigning a new value to B, means A and C stay the same, but then the contents of A moves over to B. And now B and C stay the same, and the contents of C goes over to A. Why is that so awfully complicated? And for a trivial task. That is because not only do we have 3 different kinds of states where we actually don't, we only care about 2 states, but we have to manage 3 of them. The problem is that these assignments, so the first 3 are definitions, but then come assignments. Assignments introduce the notion of time. The world before the assignment and the world after the assignment. This is how time gets into our programs. And it means not only do we have to care about 3 different states, we have to care about 3 different states at 3 different moments in time. This is a total of 9 different states. And your short-term memory is likely to capture like 7 or so, plus minus 2. For me, that's typically 5. I can tell, you know. And the problematic part, this assignment, and in the middle, you know, A and B is 1 and 1. I mean, it's not even wrong. It's not only wrong, it's inconsistent, even worse. So somebody from the outside could say, well, A and B, 1 and 2, or 2 and 1, even if we are okay with that. Any observer from the outside sees inconsistent states. But even without the inconsistency, even if we can hide this, at one point in time 1, he sees 1, 2. At a second point in time, he sees 2, 1, which is correct. Yesterday you said 1, 2, and now you're saying 2, 1. Are you lying to me or what? Right? That's the kind, you cannot really reason equationally. You can only reason operationally in the run of events. That's called operational reasoning. And this is what makes our programming so difficult. I mean, we are a self-selected group, right? People that have difficulties with this kind of thing, they don't stay in programming. They have left, right? So we are kind of the weird people that have no problem with this. Until we realize that, you know, this is an object with 2 parameters, and I switch the parameters, and now they're switched, and the other one is looking at it in parallel thread, and then it comes, you know? Then it comes. Here's the second way of going about the same task. We're using functions. A is 1, B is 2. And here's what we do. Nothing. You know? A stays 1, B stays 2 forever. We never ever change it. No question who looks at what time, it always stays the same. There is no assignment. Case closed. But, thank you. Yeah, spare a little, it comes. So, but then the question is, but how do I see the different state? You know, the swapped state, how do I see that? Well, seeing the other one is easy. You only need a pair of glasses with this prism inside such that you see it like so. It's pretty easy. This is our glass. We look to the very same memory location, whatever that is, through our prism glasses. Right? Swap AB equals B, A. Now is the time for clipping. So that's it. Actually, I have been telling this lately to my parents when I visited home, and they asked, oh, well, boy, what are you doing? And I said, well, make this thing here where we have these two glasses, and then we switch them around, and then we found this new thing that you can just look at it differently. And they got it, right? They fully understood it. And my mother is 75, and my father is 80. And they have no technical background whatsoever. They can barely use email. So they got it. Even our marketing staff got it, you know. They wanted to hear about it, and it's even more surprising. So when the next senior Java engineer comes to me and says, I don't understand this functional programming, that's too complicated, I say, well, you know, maybe a career in marketing would be something for you. So it's not so difficult. Actually, it's much easier. It's much easier to reason about the code. Now, if that is easier, if we can get rid of these assignments, well, maybe we are free to use them in Java. And so we could just leave them away, and we sometimes do. But if we had a language that forces us to go the functional way all the way down, by simply removing assignments from the language. You know, there's no more assignments in the syntax. You cannot even express this. There's still an equal sign for definitions, but there's no assignment. And assignments are only a special case of statements. It's a special case of a side effect for changing something. So just statements also go. No statements, no assignments. No more problems. Yeah. No more problems, that would be the idea. Question is it still practical? Can we still work with that? The practical part is more tomorrow. Today is, do we really want to do this? Do we really want to go this route? Let's remove statements. What do we gain? What would be a typical gain? We gain pure functions. Functions that only rely on the parameters that they get, on the arguments that has been passed into them, and they produce no observable side effect whatsoever. They do not mess with any state, and they return a value. That's a pure function. That's a mathematical function. Well, there are not many languages on the JVM that can actually guarantee this behavior. And let's start with Java as a typical example of these languages. Let's say we have here the type signature foo, some method. It takes one argument, a p, which is of type pair t and u. Who in the room is a Java programmer? Everybody, thank you. That was for calibrating myself. It was 100%. So I guess you understand what that code does. It returns something of type t. Actually, or maybe a subclass of T, you know. Co- and contravariance thing is difficult, actually. Anyway, so what could foo possibly do? What could happen when I call foo? Everything under the sun, thank you. Everything can happen. You have no idea what happens. Well, it's kind of likely that it tries to return the first element of the pair, but it could return null. Could throw a null pointer exception, could do some log statements, could go to the database, launch the missiles, whatever. You cannot tell. The same in Frege, the exact same thing in Frege, actually almost same thing in Frege, is we do have a function now, not a method, but a function foo. The double column reads as is of type. And the type on the right-hand side is a function, as you can tell by the minus greater than. It takes round parentheses, means it's a tuple, 2 elements, so it is a pair of some types alpha and beta. It's lowercase characters, means it's type variables. It stands for some type. For all types A and for all types beta, it returns an alpha. What could possibly happen when I call this method? When I call this function. When I apply this function. So there could be a general existence error of the universe, okay. But other than that, it can only return alpha in a value of type alpha, a value of that alpha type. And why is that? First, there is no null, it cannot return null. It cannot throw an exception, it's not declared here. Could be, can do it in the type. There is no possible way that you can call anything on that alpha because we don't know anything that we could call on alpha. Not even a toString or an equals or whatever. We can certainly not construct any value of type alpha. So in the end, in Java, any kind of these languages, everything can happen. In Frege, alpha is returned, and we can rely on this. This is reliable. With these pure functions that we have, we can cache the return value. We have all kinds of optimization options currently, at once, suddenly. We can cache the value. Oh, let's go back again. So since A and B never change, when we look through the glasses, the result never changes. It cannot possibly change. We can cache the value. We can cache the return value. It cannot possibly change. So with a pure function, you can, it's called memorize it, right? You can, wait with the evaluation, with the applying of the function until somebody actually looks through the glass. Lazy evaluation. You can speculatively say, well, my computer is idle, has nothing to do. We can spawn a separate thread and speculatively apply this function and see what happens and cache the value, right, in advance. And that means you can do things concurrently, safely concurrent, safely in parallel. This is big, doing things safely. And then when you have a program, lines and lines and lines, and you see the same expression, like swap AB in various places, you can do the exact same thing as in school mathematics. Say, well, multiple times, same occurrence, I just remove them with, this is an A, I just replace it with A in every piece, right? Elimination of common sub-expressions. That's actually, your code becomes algebraic. You can work with your code as if it was mathematical functions, including algebra. So there's many, many ways to optimize the code. This is nice. I want to have that. Can I do this in some other language? Let's say Java. Let's say I want to call some method in Java concurrently. What do I have to do? I have to check for thread safety. Okay, if it is immutable, if it's a pure function, it's thread safe. Okay, so what do? I go into this function. Okay, it makes A, B, C, 3 statements. What is A doing? A calls AA. Okay, A calls AAA. Okay, so we go down, and you're in this situation. And then you have a large call tree. And who has ever been in a debugging session? Who has ever been in any okay, everybody, thank you. So this is actually org hibernate EJB3 configuration add classes to session factory, which calls EJB configuration configure, which calls with a persistence info and a it is crazy. It has a recursion pattern in it, so it's not quite as bad as it looks. Anyway, you have no chance of knowing, and it's really lots of work to see whether something is pure or not. And then you have convinced yourself it's pure. You check in, you call it concurrently. Some other programmer makes a change to the code base. somewhere. And now you reassess this again, because something could have happened. Well, you would need to, but you don't know. The idea is we let the type system find out. When a language like Frege is able to tell you whether a function is pure or not, and it carries this information in its type signature. So if the type signature says it's pure, you can absolutely rely on the purity. It's an absolute guarantee. How cool is that? And even if it's not pure, it tells you what kind of impurity that is. Does it do a state change? Does it do I/O? Does it go to a database? Is it manually some GUI stuff? Whatever, it tells you. Yeah, it's pretty cool. You can rely on your code. I like this slogan. I've seen this slogan outside. In code we trust. I'd like to copy that. I find that cool. Anyway, now comes a problem. We can have the nicest language, but we live on the JVM. Now all these languages that live on the JVM and provide additional benefits, they need to interoperate with Java. You would like to leverage all the libraries that are there in Java. You'd like to call into your own homemade code and so on. You want to reuse it. And then most of these languages, pretty much all languages that I've seen so far, except Frege, they call totally unprotected into Java. They have new guarantees, either compile time guarantees or runtime guarantees, but once you call into Java, they're all gone. How often do you call into Java? Like every second line, right? So that kind of renders these guarantees totally impractical. The idea of Frege, and this is the first language that I've seen that is doing this, is not to mix object orientation and functional programming in this regard and call unprotected in Java. It allows a combination, but only with clear demarcation where things are still pure and where they aren't. So there's one way for calling Frege from Java, which is not so interesting. Here's the interesting one. If you're inside Frege and you'd like to call a function like encode Dierk Koenig, this encode is from the URL encoder in Java, JavaNet URL encoder. If you want to use this Java method, you have to declare it on the Frege side in Frege terms, in these very rigid terms, saying it is a pure native code. We have inspected it. We know it's pure. Its type is string to string. Even sometimes Java is pure. So from the Frege side, we are free to optimize it in any way. We can cache it, we can call it concurrently, and so on. There's other ones, like Java Lang System current time millis. Can we cache that every time we call current time millis? If we cache that, not so nice, right? So the type of current time millis from Frege perspective is from unit to not to a long, but to I/O long. It is reading the system clock, which is an input, so it's an I/O related activity. It's an action. We can call it with. Now we say it does not care the pure keyword here. We can call it millis, and millis we get new millis. It's not cached. The system knows that it's no longer cached, cannot cache. And if we try to somehow do something with these millis, like say -1000, this doesn't compile because millis does not return a long that you can do arithmetic with. It is an I/O long. That means you have to enter this I/O context, put yourself into the I/O context, then you can read that value, calculate with this value, but since you're in the I/O context, you're I/O connected again. And whoever calls you can only get onto your value if he also enters the I/O context. So the caller, they must all be in I/O, in the I/O context. Once somebody is impure, once he's tainted in that way, this percolates up the call chain until your main method. Right? A little bit like exceptions were in Java. So Frege can call to Java, but never unprotected. You don't lose the language guarantees when you call in Java. It's a little bit more, it's a little bit of extra effort, people say, to do this. But you know, you have to pay this effort anyway. You have to make that rationale. Yes, please?
Question, because I maybe missed it, but the question is, I understand that you can wrap the value.
1 second, just could you wait for the microphone, please?
Maybe I missed it, but I understand that you can wrap the value inside I/O, but how do you deal when Java throws an exception or returns a null?
Yeah. So there's many. Sorry, the question was how deal with null values? How do I deal with exceptions? When this code throws an exception, let's say current time millis can throw an exception, then the return type is not a plain value; it's the so-called either type. It's a union type, right? So it is either the I/O value or the exception, and the caller has to care about it. The caller cannot just ignore that there may be an exception. He has to care for both cases. The callers must do this. If it may throw if maybe it throws a null, then the return type here is the maybe long. And then it's either just a value or nothing. Right? It's like optional types in Java 8. 1,000 times better than optional types in Java 8. But I keep it at that. Thanks for the question. So it is, you do this never unprotected, and all the effects are exactly as explicit as in Haskell. Actually, Frege is a Haskell. It compiles Haskell code. So the type system has a huge number of additional benefits. The most important one is global type inference. Many languages claim to have type inference, and in Java it means you don't have to duplicate things on the same line twice, like so, right? This is kind of I don't even call this type inference, that you can do this in the parser if you want to, right? But and then there's local type inferences that some languages have. So once you know the parameter types, you can deduce what the return type should be. Right? And inside a method, you can do this. But Haskell and Frege has global type inference. So you write a piece of code, then Frege has some idea what the type of that code is. Let's say for every single expression in your code, and code is only built from expressions, for every single one, it knows exactly the type and checks it against the type that you have provided and tells you about errors. Every single line of code, we'll see this tomorrow, is statically typed. But in most cases, in the vast majority of cases, you don't have to tell anything. It will find it out on itself. So less work, but much more safety for the programmer. In fact, some people may know that I did a lot of work in Groovy. Groovy is a dynamic language. And you're free to provide as many type information as you want. But if you don't, then things are just object, which is fine for many reasons. But here, it's kind of the same. You decide how much information you want to give extra, but then if you don't give the information, it gives you the least upper bound, the least amount of constraints type-wise that will still make your code compile correctly. So that's actually the best type system that I've seen so far. And the typical effect is like so. You have some piece of code runs from top to bottom. It's like your stack, right? Time flows from top to bottom, and the stack is from left to right. These green ones are pure computations. And these pure computations may live, they are islands in the sea of mutable stuff, right? You have database and I/O and whatever, and some mutable state, but inside the state there are pure computations, the green ones, that you can rely upon. All the green ones and the compiler can figure this out by itself, are thread safe by design. It's checked by the compiler, it's guaranteed. And the other ones outside, they also follow the same language characteristics, but they may carry information, extra information. So these things are called monads. Be brave. They don't bite. The thing is, this is unescapable, right? You cannot escape. Once you're tainted, you cannot escape it. And in fact, if you do some Java project and you'd like to introduce Frege, a good way of doing this is kind of this same picture, but if you follow a service API, service-based design. And service is not necessarily a remote service, not necessarily like microservice design, but it can be in the same VM. It can also be remote if you want. So you're calling into pieces of code that only work on their arguments and return a value, do nothing else. So I'd like to show you some, we will reprogram this tomorrow. But for today, I'd like to show you only the one piece of code. How does it look like, and how is that different? And who has ever heard of FizzBuzz? FizzBuzz is like, okay, not so many. It's kind of a children's game or drinking game, or maybe. So, drinking game with your children. So, it goes like so. You have to count 1, 2, 3, 4, 5, 6, 7, 8, and so on. So for every third number, you have to say fizz, 1, 2, fizz, 4, 5, fizz, and so on. I'm not so good in this game. So, and for every fifth number, you have to say buzz. 1, 2, fizz, 4, buzz, and so on. And then comes the point where the third and the fifth, like at 15, you have to say fizz buzz. So, okay. And there's this kind of a typical test that people do when they're assessing you programmers, for example. So here is the typical Java. When you Google for this, FizzBuzz, here's the typical Java solution that you will find. That's Google #1 hit for the Java solution. Okay, you're a Java programmer. It actually works, right? Looks good. Anyway. It's a little bit complicated, and I'd like to draw your attention to how many state changes there are, like 100, and then how many conditionals, and then nested conditionals, and then what to do, how often that comes out here. So it's quite some. Yeah, it's kind of the code that I would have written a few years ago. And here's the one that we will end up tomorrow. And we'll take it line by line. The first one is we make a list, and it's a literal declaration of a list. An empty string, and a fizz. And this cycle function takes a list and makes an endless repetition of that list. So it goes empty, empty, fizz, empty, empty, fizz, empty, empty, fizz, forever. Next one, same with buzz. 1, 2, 3, 4, buzz, and so on. Now comes the zipping function, which takes 2 possibly endless lists and zipping them like a zipper together with a function. And here the function that we use is ++, which is string concatenation. So the pattern is actually empty, empty, fizz, empty, buzz, empty, fizz, and so on. Actually kind of complicated. So the pattern is an endless repetition of exactly the pattern that we like to superimpose on natural numbers. And how do we put it onto the numbers? With zipping again. We make the endless list of numbers, it's written like so, and the pattern, it's an infinite production of these patterns. And the function that we're zipping it with is a combination of show is to string in our terms, and getting the maximum. Now the maximum on strings happens to be exactly what we want, because 1, 2, 3, 4, 5, and so on is always smaller than everything that's fizz or buzz. Anyway, so that's kind of a Java thing, really. So we have FISBUS. FISBUS is an endless repetition of our pattern that we want to print out. And we can say, well, take the first 100 or take any slice of that and use it. Let's compare. There is no conditional whatsoever in the logical code, but 4 in the imperative code. There are 7 operators, and in the logical code, there's actually no operator. But the plus plus, well, take it as an operator if you want. Well, it's actually a function call, but I give you that, right? Nesting level, 0. You know, conditionals and operators in nesting, I immediately know that I will do an error there. And then when you see the Java code, it's very sensitive to reorderings. For example, if you don't do the check for 15 in the very beginning, but later, code gets wrong, right? Here you can reorder it in any way you want, stays the same. Now let's say maintainability. Now let's say Java code. Every 7th number should now be foo. And multiples of 1, 3, and 7, and 5, and 7, and 3, and 5, and 7 combined, in which order? And then, yuck. Yeah. Now we would like to not go system out println, we would like to go system error println. 4 different lines to adapt. Very difficult. Here, println, system error println. Have another rule, make another rule, and another zipper on the pattern. That's it. Remove one, remove one. Much easier to maintain. So this looks all already promising, but you know, with this kind of programming without statements and programming without assignments reminded me when I first heard it about my first experience with Java. They said, Java, you know, Java has no more pointers. And I was doing C and C++ at the time. You cannot possibly program without pointers, right? That was my thing. But then I learned there are no more pointers but references. You can still have null pointer exceptions that make me good. So the case is a bit similar with Frege and Java. There's no more state in Frege, but you know, there's ways of making it look as if there would be state to make it more comfortable to work with this kind of scenario where you pass values around. There's no more statements, you know, no state, no statements. It's kind of, yeah, it's not by coincidence that same word here. But we do have expressions and special kinds of notations that make the code look as if there would be statements. There's no more assignments, no more variables that can change any state and so on. So there's no more null references, but we have this maybe thing that we have to care about. But the compiler tells us when we forgot to care about it. So that's the comparison. And well, to put it somehow in context, Groovy in Java and Frege and Haskell, this is by Simon Peyton-Jones, this concept, the main mind behind the Haskell compiler, the most prominent one. And he said, well, Haskell is totally safe in the way that it only applies logic. It's less practical. It's not, you know, we'd like to do something with our engine that we have here. We're engineers. We take the engine and do something with it. In Haskell is more we have a thought, and we'd like to somehow impose on that thing. You need to make it practical. And Frege tries its very best. That's the goal of the project, to make it approachable and useful for the Java programmer. A totally new level of safety that you have in your code. It's very relieving. You get code that is very robust under parallel execution. That's big. That's very big. I'll talk more about that tomorrow. But But also, it's even on the smaller scale, let's say composition. Imagine you have a library. A library has a function like URL encode, javanet URL encoder .encode. That's your library. You have to pass it a string. Do you hesitate to pass it your string? No, not even. You don't even consider to be careful with your string. Why? Because string is immutable, right? You can pass a string anywhere. If it was a person object or a list or anything, passing it to some method, may change it, may reverse it, something, you don't know. So if you program with immutable values, you get robust composition. Same is true for increments and refactorings and so on. And a language that enforces this is the best language to learn functional programming. Even if you later apply functional programming in Java or any other language, for learning it, it's really good if it keeps you nice and tidy with your code and say, you cannot do this, right? You have to think differently about your solution. So that best way to learn FP. I can totally underline that. So how do you learn functional programming? Well, you effectively learn Haskell. You can take any of the books, any of the tutorials, courses, YouTube videos, what have you. There's loads of that. Also, these books are very good. There's a special one with some exercises, I would say, in Frege. And just this week, on Wednesday or Thursday, I'm not quite sure, there starts a massive online course on the edX platform. It's free of charge. If it costs like $50 if you want to have a certificate, I guess. Run by Eric Meyer, who makes an excellent job of explaining functional programming. It's not an easy course. It's rather time-consuming, and in places it's actually rather challenging. But you will learn functional programming. And the trick is, most of the code is in Haskell, but I made all the various exercises and homework assignments and so on in Frege as well. It's almost no work. And so you can work in Frege on the JVM and do this course. That is highly recommended. Why did we call it Frege, this language? I'll jump over that. Maybe tomorrow. And if you'd like to hear more, if you'd like to see whether it's really practical, how do I program with pure functions, then I'd like to see you tomorrow afternoon in the tutorial. Do we have a few minutes for questions? We are a little late. Let's